All right, so for problem 9, part A, it asks, well, we're given this equation, this formula, and it asks for the initial mass of the rock. And so that's just going to be m at time equals 0, right? Because that's where it's initially at. And so we just plug 0 into the equation, and then we'll get 18.8 grams, because the equation is mass of a rock in grams after t years. And then if we draw this out, we'll get something that kind of is like, well, we'll have like this horizontal asymptote at 15, and then we'll have this end behavior as t approaches infinity. It's just going to keep approaching that 15. And so we'll just say as t goes to infinity, m of t goes to 15 grams because of horizontal asymptote. So in problem 10, we are given a population with 1.22 billion people in 2013, and it grows at a rate of 1.28% per year. And it wants us in part A to write a formula for the population in billions as a function of t years since 2013. So we have our initial population is 1.22 in billions, right? And then our rate of growth is 1.28%, so we just convert that to a decimal and add that plus 1, so it's going to be 1.028 or 1.0128, right? So then we can write our formula. We can write our formula as P of t equals 1.22 1.0128 to the t billion. And then it asks in part B, by what percent did the population of India increase in the 2-year period between 2013 and 2015? So we'll just plug in 2 for our t, because that's 2 years, right? And then we'll get and so then we'll take 1.0128 to the second power, because that'll be like our growth between those 2 years, right? And so then we'll get a growth of 1.02576, and we'll subtract 1 from that, and then multiply multiply that number by 100 to get it as a percentage, and we should get the decimal 0.02576 or 2.58%. All right, so number 11 will be kind of similar to 10b, but it says an investment decreases in value by 5% per year for 4 years, and it asks by what percent the investment decreases over the 4-year period. So that's a decrease of 5%, so we're going to, I guess we would do 1 plus negative 0.05, right, which would give us 0.95. And then for 4 years, we'd take that to the fourth to find, I guess, our growth factor, right, or in this case, our decay factor, which is 0.814506. And so we want to keep it positive, so instead of doing minus 1 like we did in part B, we're going to do 1 minus that, because that'll give us a positive. So then we'll get 1 minus 0.814,506, which gives 0.18549, and then if we convert that to a percentage, we'll get 18.55%. All right, so number 12, we have a population of ants that grows at a continuous rate of 6.2% per month, and the initial population of ants was 200,000. And so we have to write a formula for the population of the colony at t months. And so we got our initial, and with this being continuous, that's going to be an initial value times e to the kt, right? And so we have our initial value of 200,000, and we have our continuous rate of 6.2%, or if we convert that to a decimal, 0.062. And so our formula is going to be P of t is equal to 200,000 e to the 0.062 t. And so then it asks by what percentage does the ant population increase in 2 months. And so what we're going to do is we're going to take e to the 0.062 times our 2 months, and that's going to give us like a growth of 1.132015. And so to find it as a percentage, we subtract 1 from that, and then we multiply by 100, And so then we'll get an actual percent of 13.20%. Okay, so for 13a, if we're going to simplify this expression, first we know that if something is out in front of a log, we can take it inside the log, but it's going to be an exponent, right? So then that 3 log x turns into log x cubed, and then that means our log of y, 2 log y, can turn into log y squared, right? And we also know that if we have logs added together, we can multiply what they have inside of them and take it as 1, right? So then we'll get 10 log of, remember I said x cubed, and that's going to be times, actually, let me rewrite that, make it look prettier, times y squared. And then we know that these just go away, and then we have y cubed, or x cubed y squared. All right, so on part B, we're given a lot of natural logs and e's. So this natural log and this e can kind of cancel each other out. So then we're just left with natural log of square root of x minus 5 natural log of x. And we can do the exponent rule, like I said before. So that square root of x can be rewritten as x to the 1/2, right? And then we can bring that 5 inside. And so that's going to be natural log of x to the 5th. And so then we'll have natural log of x to the 1/2 minus natural log of x to the 5th. And whenever you subtract the logs, that means you can divide them by each other, right? So that's going to turn into natural log of x to the 1/2 over x to the 5th, and which can simplify to x to the negative 9/2. And so then once this simplifies to x to the negative 9/2, we can bring that exponent back out, right? So then to fully simplify it, we'll have natural log, or negative 9/2 times natural log of x as our simplified one. Okay, so for number 14, we're given a graph of log base 4 of x, and then we have some transformations that are being applied to it that we have to graph. And so it looks like by these transformations, that negative tells us that we're going to be reflecting across the x-axis, and then this plus this x plus 2 within the log means we're going to shift it left 2 units, right? So then what we can do, and we know that our asymptote for a log base 4 function, we have a vertical asymptote at 0, right? Which means our vertical asymptote is also going to shift left by 2. And so then if we reflect this over the x-axis, and we got to shift it left 2 units, then we'll have a function that kind of looks the same, with just a little bit of tweaks to it. And so the domain and range of this new function, well, we can tell that it doesn't go, for the domain, it doesn't go beyond -2, right? It is capped at that -2, but it can go to infinity. And so our domain is going to be -2 to infinity. And then our range can be anything, right? We can see that as it's approaching this vertical asymptote, it's going to positive infinity. And then as it's going to infinity for x, then it's also going to negative infinity for our range. And so we'll just say our range is from negative infinity to infinity. And then part C asks for the vertical asymptote, and we just said that our vertical asymptote shifts left 2 units, right, with the transformations applied to this function, and so our vertical asymptote will be at -2. Okay, so on number 15, we have to solve for x, and give our answer in exact form, and then round it to 2 decimals. And so for part A, we have this natural log, right, and we want to get rid of that. And so we'll just take e to the both sides, e to the power on both sides. And so that gets rid of that. And so we're just left with 10x plus 1 is equal to e squared. And then if we're trying to get x by itself, we can just subtract 1 over, and we'll get 10 to the x is equal to e squared minus 1. And then we got to get x. We got to get x out of the exponent, right? And so we can just take log base 10 on both sides, And then that'll leave us with, we can bring that out in front, and so that's going to be x is equal to log of e squared minus 1, or that's going to approximately be 0.81 if we round to 2 decimals. On part B, so if we want to solve for x, we want to get it by itself, but also have it on the same side, right? And yeah, we're trying to get it by itself. So in order to get it by itself, we can divide 7 on both sides and also divide by 3 to the x on both sides to get the x's on the same side. So that'll leave us with 8 over 7 is equal to 4 to the x over 3 to the x. And so since the 4 and the 3 are both being taken to an x power, we can just factor that out and say 8 over 7 is equal to 4 over 3 to the x. And now we want to get x out of the exponent, and the best way to do that is to either take both sides to the natural log or take both sides to the log. And so if we just do natural log, if we do natural log on both sides, that'll give us natural log of 8 over 7 is equal to, and remember, whenever we take the natural log on this side, we can bring that x exponent out in front. So that's going to be x natural log of 4/3. And then if we divide on both sides by natural log of 4 over 3, that'll leave us with x is equal to natural log of 8 over 7 over natural log of 4 over 3, which is actually approximately 0.46. And then if we come down to part C, we have logs that are being added together. And remember, when we have logs that are added together, we can take what they have inside and multiply them. And so that's going to be log base 2 of x times, x minus 7. But I'm just going to go ahead and FOIL that out, and that's going to be x squared minus 7x, right? And that's going to be equal to 3. And so what we can also do is to get rid of that log base 2, we can take 2 to the exponent on both sides, and so that's going to leave us with x squared minus 7x is equal to 2 cubed, which is 8. And then we can subtract this 8 on both sides to make this into a quadratic that we can solve, because that's going to be x squared minus 7x minus 8 is equal to 0. And so if we solve that quadratic, we'll get x plus 1 and x minus 8 equals 0. And so then if we solve, we'll have two separate solutions. We'll have x equals -1 and x equals 8. But remember, we cannot take the log of a negative number, right? So we have to make sure that both of these solutions don't give us a negative, like we're taking the log of a negative. And so if we look at this -1 right here, we would have to take a log base 2 of -1, which we can't do. And so I'm just going to cross that out and just say that's extraneous, because we can't do that. And so we'll just be left with x is equal to 8. All right, so for number 16, we're given a function for a population of turtles after t amount of years. And so on part A, it says the second time the turtles were counted, their population was 250 turtles. And so it asks how many years had passed after the initial count. So we know we're solving for time t because it wants to know how many years, and it gives us a population. So we'll have our equation set up like, 250 is equal to that original formula they give us, right? And so it's going to be equal to 175 e to the 0.045t. And so then if we're trying to get t by itself, we can divide by 175 and then take the natural log. So if I write that out, that's going to be e to the 0.045t is equal to 250 over 175. And then we can take the natural log of both sides to get rid of that e. And so then that's going to be 0.045t is equal to natural log of 250 over 125, or sorry, not 125, but 175. 175. And then if we divide by 0.045 on both sides, we'll get t is equal to the natural log of 250 over 175 divided by 0.045, which gives about 7.93 years. And so on part B, it says assuming a population of turtles grows at that same rate, so that means we're still going to have the 0.045 rate. And then it says, by what percentage should the population increase in a decade or 10 years? And so what we're going to do is we're trying to find how much it grows, or it's like growth amount. And so that's going to be, we're just going to have that e to the 0.045 times the 10 years. And so that'll give us a growth of 1.56831, but to get that as a percentage, we have to subtract by 1 and then multiply it by 100, right? So then once we do that, we'll get a growth percent of 56.83%. All right, so on number 17, we have a tennis ball that's shot vertically upward from a height of 6 feet above the ground. And it says at time 3 seconds, it was at its highest point of 177 feet above ground level. And so we have to find a quadratic formula for that, and so for the height of the ball. And so if we have something that's shot up like a ball or whatever, vertex form is usually the best to use because we know that it goes up and hits a high point and then it has to come back down. And so, it even says right here at a time 3 seconds, it was at its highest point of 177 feet above ground level. So that's its highest point. So we know that it must be a max, right? And so we can use vertex form, which is, that's going to be h is equal to, if you look at the formula, we'll have a, and then we'll have t minus, well, our vertex is at 177, right? Vertex. And so that's going to be t minus 3 plus 177. And we're also given another point. So it said it was vertically shot upward from a height of 6 feet above the ground. So that means like at t equals 0, height was 6 feet, right? And so to solve for our a value, we can just plug that point in. So that's going to be 6 is equal to a times t, not t, because we have a value for t, right? It's 0. So it's going to be a times 0 minus 3 plus 177. And so then if we solve for a using that, we'll get an a equal to negative 19. And so then our actual equation will be h is equal to negative 19 times t minus 3 plus 177. And then it asks for, it asks in part B what the height of the ball was at 5 seconds. So then we can just take h of 5 for the formula that we just came up with. And so that's going to be 101 feet. Okay, so on number 18, we have to find certain things for a polynomial. And so on part A, we have to find the leading term and degree of f. So that's going to be our, well, if we factored all this out, that's going to be our x value that's to the biggest power. And so we know that we're going to have, well, we have this negative 5 out in front that's going to affect the term, right? But then 4x is our biggest x power in this parentheses, right? So it's going to be 4x to the 5th. And then our biggest x in this parentheses is 3x. So that's going to be times 3x to the second power. And so then if we square this, that's going to be 9x squared. And then that's going to be 4 to the 5th times x to the 5th. And then we'll have negative 5. And so if we evaluate all of that out, that's going to be negative 46,080 x to the 7th. That's our leading term. And then the degree of f, our function, is going to be the greatest degree. And so our greatest degree, like we just said, is equal to 7. And then on part B, we have to find the zeros and their multiplicity. And so multiplicity is the power that each parentheses is being taken to. So we have two different parentheses, right? And two different values that we can solve for zeros for x. We'll have 4x minus 3 is equal to 0. So if we solve for x, it's going to give us x is equal to 3/4. And since it's being taken to a power of 5, it's going to have a multiplicity of 5. And then we'll have our second parentheses, 3x plus 1 equals 0. And if we solve for x, we'll get x equals negative 1/3. And that is a multiplicity of 2. So then we have to look at their long run behavior, right? And so we can do that by looking at the leading term. And so we know that x is being taken to a 7th, so which is an odd power, right? So the end behavior isn't going to be the same as x goes to negative infinity and x goes to infinity. And also it's negative, and so it's going to kind of do the opposite of, you see we got that negative in front of the coefficient out here. And so that means that as x goes to negative infinity, f of x will go to infinity, and then as x goes to infinity, f of x will go to negative infinity.